Hello, and welcome back to College Algebra, MAT 150. In this lecture, we're going to talk about the rational zeros theorem. So, what is the point of the rational zeros theorem? Why do we want to talk about it? Well, in section 4.2, we talked about graphs of polynomials. However, to get the graphs, we had to talk about the zeros and find the x-intercepts. And to do that, we had to completely factor the polynomial. And then in 4.3, so sometimes that can be difficult. And in 4.3, we actually discovered if we divide by a known factor, then we're going to get another factor, which is the quotient. Okay, the problem, and maybe the quotient we could factor more easily, but the crux of that was that we had, where it was limited, is that we had to know the factor ahead of time. So the rational zeros theorem gives us a way to possibly guess what those factors are ahead of time. So if we look at the polynomial with the leading term, a sub n x to the n, with the leading coefficient being a sub n, and the constant term a sub 0, or a naught, you may hear me say. And if we look at the factor, if we look at a factor of a naught, and a factor of a sub n, so r is the factor of a naught, t is the factor of a, then plus or minus this fraction, this r over t, those factors over the factor, are possible zeros. And again, emphasis on possible zeros. And when we say zeros, we mean that if you plug them in, it makes the output of the polynomial is 0. So this gives us all possible zeros, and they're all rational zeros. They're never irrational numbers. So it doesn't give us all the list of all real zeros. We could also not get, we could get complex zeros or imaginary zeros. And since they're possible, it's not guaranteed. In fact, you can only ever have at most n zeros. You can't have more than that. And the list that we could make could far exceed the number of actual possible zeros. So, let us look at this. So given f of x equals 3x to the fourth minus 11x cubed plus 10x minus 4, let's find a list of rational zeros and determine which are actual zeros. So as it turns out, so we want to find the possible zeros, we look at the rational zeros theorem, and we look at the coefficient of the leading term and the coefficient of the constant. So 3. And we can say negative 4, but we really just need to focus on the numerical part. We don't need to care about if it's negative or positive. So 3 is, what are factors of 3? Factors are things that divide evenly into this number. Well, only 1 divides evenly in 3, because it's a prime number. 4, however, we can divide by 1, we can divide by 2, or we can divide by the original. So it's not prime. So, what are the possible zeros? Well, all possible rational zeros. And this does give us a full list of all rational zeros. Again, rational numbers are just fraction numbers or integers. And it's this number, these numbers, over this number with a plus and minus. So let's say 1 over 1. Plus or minus, 1 over 3, plus or minus. Now let's go to the next one, 2 over 1 and 2 over 3, plus or minus 2 over 1, plus or minus 2 over 3. And then we also have 4 over 1, plus or minus 4 over 1, then plus or minus 4 over 3. We can rewrite this list to make it look just a little bit nicer. We don't like thinking about things like 1 over 1, plus or minus 1, plus or minus 1/3, 2 over 1, plus or minus 2, plus or minus 2/3, and same with this one, 4 over 1 is the same as 4, plus or minus 4, plus or minus 4/3. All right, so what can we do with this? Well, this is a list of all possible zeros, and we want to see which one of these are actual zeros. So as it turns out, if we plug in, so the way we can do this, we can just immediately evaluate it. So let's try x equals 1. So we have f of 1 equals 3 times 1 to the fourth minus 11 times 1 to the third plus 10 times 1 minus 4. Well, that's 3 times 1 to the 4th, so that's 3. So 1 to the 4th is 1 times 3 is 3. 1 to the 3rd is 1 times 11 is negative 11. 10 times 1 is 10 minus 4. 3 minus 11 is negative 8. 10 minus 4 is 6. Negative 8 plus 6 is negative 2. And again, if this was a 0, the output would be 0. So, since it's not 0, this is not a 0 of our polynomial. However, we could also try x equals, now we tried positive 1. Let's try x equals negative 1. Sorry about that, let's rewrite that. So to see if that's a 0, we just plug it in and see if 0 pops out. So we have f of negative 1 is 3 times negative 1 to the 4th minus 11 x cubed, or minus negative 1, excuse me, cubed, plus 10 times negative 1 minus 4 equals negative 1 to the 4th is 1. So 3 times 1 is 1. Negative 1 to the 3rd is negative 1 times negative 1 times negative 1, which is all negative 1, times a negative 11 is a positive 11. Positive 10 times negative 1 is negative 10, minus 4. We have 3 plus 11 is 14. Negative 10 minus 4 is negative 14. 14 minus 14 is 0. So what is f of negative 1? It equals 0, so x equals negative 1 is, so this one's good, a 0. So we know x minus 1 is a 0, and remember that if we know that it's a 0, then we know that x plus 1 is a factor of our original polynomial, 3x to the 4th minus 11x cubed plus 10x minus 4. Now, we could go through and we could plug all of these numbers in. So all we've done is checked these two numbers. We could go through and we could check all of these. That's a little excessive. I hope you all will believe me when I say that f of 2/3 is also 0, which means that x equals 2/3 is the 0, so that means x minus 2/3 is a factor. Of f of x. Okay, so we have, and again, I'll be clear, this is a factor and this is a factor, but as it turns out, none of the others are on this list. None of the others are actual zeros. So that means that the rest of the zeros, we know from the fundamental theorem of algebra, we have up to 4 zeros. And we know 2 of them are rational. That means the other 2 are either complex or they are irrational zeros. So let's go through a full factorization. Let's actually use this in a full regular problem. Let's see if we can get this. So we want to actually try to find the full factorization of p of x, and if you know one factor of it, you can divide by p of x and by the known factor to possibly help us get other factors. We don't necessarily always have something good to be able to factor like this. In fact, if you try to factor this by factor by grouping, you will not have a very good time. However, if we divide first, if we find out what one of the factors are first, and we divide by a linear factor, we'll be left with a quadratic, which will be much easier to factor. So let's try that. So all possible factors. So we want to look at 1 is the leading term here, so we have to determine our factors. So the only factor of that is 1. We also have 12. This one has a couple though. So we have 1, 2 divides into 12, 3 divides into 12, 4, 6, and then 12. So, by the way, since these are all from the coefficient, they're always divided by factors of this. You're dividing by 1 in each of these cases, so all possible zeros are plus or minus 1. Again, it's always over this 1, so it's always just going to be these numbers, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12, and yeah, so we have an ultimately 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possible zeros, and we could clearly only have 3, okay? So we just have to pick one that works. So let's see, let's literally try some of the easier numbers. Let's try 1. So f of 1, if we plug that in, 1 cubed minus 2 times 1 squared minus 11 times 1 plus 12. That's 1 minus 2 minus 11 plus 12. So that's negative 1. And negative 11 plus 12 is, so 1 minus 2 is negative 1. Negative 11 plus 12 is positive 1. That equals 0. Hey! F of 1, so 1 is a 0. So x minus 1 is a factor. So the way I got x minus 1 was by bringing this one, getting this one side equal to 0 by subtracting 1 from both sides. All right, so now that we know x minus 1 is a 0, because, or x equals 1 is a 0 because x minus 1 is a factor, excuse me, then that means that we can do division. So we can divide this factor into this factor. Now you can do polynomial division, or because this is a nice factor, we can do synthetic division. So we're going to divide 1 into, what are the coefficients? 1, negative 2, negative 11, 12. 1, negative 2, negative 11, 12. How do we do polynomial division? We bring down the first term, multiply, add, multiply, place, add, multiply, negative 12, add, we get 0. And this polynomial would then be x squared, 1x squared, minus x, minus 12. So it's a polynomial of degree exactly 1 less than what we dealt with, what we started with, an x cubed, and we got an x squared. So what do we know? F of x, which equals this whole polynomial, is also equal to the factorization. It factors into this factor times this factor. So we get x minus 1. So f of x is also equal to x minus 1 times x squared minus x minus 12. And now that we have it to this, we have it factored already once, we can factor this now as a trinomial, which we have other methods for. And what is x squared minus x minus 12? What are two numbers that multiply to be negative 12 and add to be negative 1? Well, positive 3 and negative 4 multiply to be negative 12 and add to be negative 1. So x plus 3 times x minus 4. And that is our full factorization of f of x. Now to be clear, we got lucky that literally the very first thing that we picked, again, always try to start with easy numbers if you can, but we got very lucky that the first number we picked was a 0, which meant that x minus 1 was a factor. So for we put the 0 there. So for our synthetic division, we went through, found our synthetic division, which meant that f of x factored into this, and then we factored this whole thing. Sometimes this part you may have to do more here to find the zeros. So you may have to do this, you may have to do f of negative 1, f of 2. You may have to go through a list until you get all the way to the end. But the moment you find one, that you can then break it up and then see if you can factor the next polynomial that you get. This concludes this lecture.